Okay, so let's get started. We're going to be taking a look at working with setting up our volumetric efficiency table within our model fuel equation mode. This is pretty straightforward to do. There's some rules, so to speak, in configuring and setting up the table for the actual values found within the table. We want to make sure that the breakpoint scaling makes sense for our engine and application, meaning if the engine's spinning out to something like 9,000 RPM, we want to make sure that we have our engine speed scaled correctly so it represents that engine speed in the table. We also want to make sure that we're accounting for whatever the induction type is going to be for our engine, whether it's naturally aspirated, supercharged, turbocharged. We want to make sure we're scaling the load axes in the table so it's going to be appropriate for our engine. Let's jump in here and take a look at where we can find our volumetric efficiency table and then start digging into these basic details so we understand what we're working with and how to set up things correctly. All right, let's move from our basics page here and let's jump over here to our fuel page. Under our fuel page, we have our fuel table 1. This is our volumetric efficiency table. Now you're going to notice that the table here is set up based on engine speed at the top, and then on the left axis, it's going to be based on MGP or manifold gauge pressure. Engine speed's straightforward to understand, so as the engine speed increases, we'll find that it's going to be sourcing one of the values in the table to estimate the airflow coming into the engine and therefore then calculate an injector pulse width based on our fuel and airflow modeling equation. I've talked about that pretty extensively up to this point, so you should understand how that works. I'm not going to go through all those details. This is more understanding how to set this table up. I'm going to assume that at this point you understand all that basic details and how this calculation is actually made. So engine speed, simple. What gets confusing when you start working with the link, because it is a little bit unique, most standalone systems aren't set up in this manner. You'll find that the table here is set up on MGP or manifold gauge pressure. This is a load reading into the table. So this is going to be factoring in your map pressure reading. So whether you're in vacuum or positive manifold pressure, it'll go ahead and source the values in the table according to that engine load. What's different about this and how MGP is actually calculated, it's going to be a simple calculation comparing our baro pressure to our map pressure. In fact, it's going to be map minus baro pressure gives us manifold gauge pressure. Now, you're probably asking yourself, why is this not just set to map pressure? Because that's typically what you'll find in most standalone systems. It's going to be map pressure on the left axis versus engine speed and then the lookup values in the table. The reason why Link does this, and it's actually really ingenious, it allows you to automatically bake in and compensate for any altitude changes as your engine is running. So for example, if you calibrate and you tune your engine at sea level, and then you drive up to 5,000 feet of elevation, and you don't have any barometric pressure compensation in the tune, you'll find that you start to run rich. In that situation, you have to go ahead and retune the car at the higher elevations. With accounting for the baro pressure, again, map pressure minus baro pressure gives us MGP. That allows us to bake in the baro pressure into the load axes. So if you go up in elevation and your baro pressure drops, that will then look up a different scaling in the table or a different percentage of volumetric efficiency and recorrect your fueling delivery to your engine automatically without having to worry about creating a modifier table or a subtable that's going to subtract or add fuel based on barometric pressure changes. This allows us to account for a variable that normally standalones don't account for. So really ingenious, slick way that Link implements the baro pressure compensation right into our load axes. Now, it does take a little bit to get used to working in units of MGP, but it's actually quite simple. The way I like to think about this, if I'm at sea level, and in this case, my map pressure is showing approximately 100 kPa, my baro pressure showing approximately 100 kPa, we can see that the MGP is calculated here at approximately 0. So when your engine is idling in your normal driving situations, you're going to be anywhere from typically negative 90 to negative 80 MGP all the way up to 0. That would be atmospheric pressure. Then if you start to go full throttle on a forced induction engine, you're building positive manifold pressure, your MGP is going to increase. Easiest way to think about this is 100 MGP. So let's assume again sea level to keep things easy here. 100 MGP would be the equivalent here of about 14 to 15 PSI of boost pressure. So if you're looking at a boost pressure gauge, that would be the equivalent of about 14, 15 PSI. If we have a value here going in the table up to 200 MGP, that would be the equivalent of about 28 PSIs. It's going to double. Every 100 kPa increase in MGP is essentially adding another 14 to 15 pounds of positive manifold pressure. So hopefully that's clear and it's pretty simple. Now, these units are in units of kPa. We could change this over to units of PSI. I find it a little bit more confusing. If we want to go take a look at those specific units here, we'll click U, and we're going to notice that it changes now to units of PSIA. Now, what's the note about this? This is units of PSIA. It's not PSIG. So it's not going to be what you would normally find on an actual vacuum gauge. So it definitely throws people off when you're looking at this. That's why I like to just kind of flip it over here and keep it in units of kPa. Just realize that 0 is essentially atmospheric pressure, wide open, naturally aspirated, and then anything below that is engine vacuum. You can go all the way technically down to -100. That's full engine vacuum.
Thanks for checking out our teaser clip. If you want to see the rest of this video and more than 500 hours of current EFI training we have to offer, make sure you click right here. If you want to go and check out more teaser clips from this training course, click here, and you don't want to miss any of the videos we're going to be releasing on this channel, so make sure you subscribe and click here. Thanks for watching, and I'll see you guys later.